Good morning, friends and dear students. It is my pleasure to be here again for my course Engineering Thermodynamics. I am Dr. Dwivedi, professor from Institute of Aeronautical Engineering, Hyderabad, India. As of now, I have completed all the modules, numericals and all. Now I am in the process of definition and the terminology of engineering thermodynamics of module 2. Today it is going to be the second law of thermodynamics. All the definitions and terminologies are related to the second law of thermodynamics. So here we will see that second module of I will be covering in the content. So first definition is thermal reservoir. So what do we understand by the reservoir? If you take the one sea, ocean, from the ocean if you take some 100 liter or 5 liters and all, nothing will happen to the source. You cannot imagine that there is any changes in the water level of the ocean. Same way, if the sunlight is coming and we absorb some light during our some work, the light of the sun will not change. Same way, if it is a river and you take some one bucket of water, nothing will happen to the river. Same thing, same is called the reservoir. So here we will be discussing about the thermal reservoir. A thermal reservoir or the thermal energy reservoir or the thermal bath, all are the same. So thermal reservoir is the thermodynamic system with a heat capacity so large. So a very huge, like sun, a huge amount of energy is there. So we can say that it is a reservoir. That the temperature of the reservoir changes relatively little. So if you absorb from the source, from the heat of the sun, I think nothing will happen to the sun, or it is very negligible effect will be there. When a much more significant amount of heat is added or extracted, its function as an infinite pool of thermal energy at a given constant temperature. So the energy is infinite. You know that what is the meaning of infinite and what is the meaning of zero? Both terms, that is zero and the infinite, they are the relative term. If you take the mountain or the Everest, comparing of the Everest, if you take one piece of wheat, that piece of rice is zero and the height of the Everest is infinite. Same way, when we compare with our galaxy and our Earth is like a zero and galaxy is like a infinite. So same way here, the reservoir is indication of infinite. So in the infinite, if you compare with our use is negligible. So that is the function, that is the concept of this reservoir. So example of lake, ocean, rivers often serve as a thermal reservoir. The second one is the atmospheric science. Large air mass in the atmosphere often function as a thermal reservoir, like our aircraft and all, our air is the thermal reservoir. This I have taken these definitions from this reference. So lakes and these rivers are reservoirs in geophysical processes. Now I will discuss that and define about a heat engine. So heat engine is a system that converts heat to mechanical energy, which can then be used to do mechanical work. So this heat engine, they convert the heat, and heat is obtained from some chemical sources like petrol and diesel. And this heat we can convert to the mechanical energy, which can then be used for the mechanical work. So that type of system is called the heat engine, where heat is converted to the mechanical work. It does this by bringing a working substance from a higher state temperature to a lower state temperature. So this high temperature is absorbed by this its expansion process and the work is extracted. A heat source generates thermal energy that brings the working substance to a higher temperature. So the source which is heating the air, that heat is obtained from the higher temperature, and this is called the heat source. The working substance generates work in the working body of the engine while transferring heat to the colder sink until it reaches a lower temperature state. During this process, some of the thermal energy is converted into work by exploiting the properties of the working substance. The working substance can be any system with a non-zero heat capacity, but it actually is a gas or the liquid. During this process, some heat is normally lost to the surrounding and is not converted to work. Also, some energy is unusable because of the friction and the drag. So there will be some friction, some entropy losses will be there. So these are a basic heat engine concept. Heat engine efficiency, if you see that, define heat engine efficiency. So if you see here that it is a hot source, this hot source is having a very high temperature. From here some amount of QH, the heat is taken from this, and here if you see, this is the heat taken from the source, and here heat released, discharged to sink. This is the source here and this is the sink. So heat Q is taken, QH is taken and QL is released. QH is greater than QL. So there is one system here inside this. This is called the heat engine, and this heat engine is giving some work W. So what is the meaning of efficiency? Means out of how much QH, how much work is got. It is a relation in percentage how much work a system can obtain by taking how much energy or how much heat. So that is the definition of the efficiency. This efficiency of a heat pump, eta, is equal to work out by QH. What you need. Work out means it is a output. What you need and what you pay for. So I want a work of 40 watt, but I have spent the energy of 100 watt. So 40 by 100, 40% is the efficiency of this system for this example. So it is output by input. So here how much energy is used? QH minus QL. This much energy is used in this to generate the work. So QH minus QL by QH. So 1 minus QL by QH. So you can see that efficiency will be always less than 100% because the value of QL by QH will be always positive. So if this is the positive or some number, the value of, and it will be less than 1 also, this QL. So the efficiency of the system will be always less than the 100%. Now heat pump and the COP. So what is the heat pump? Define a heat pump and the COP. So definition of heat pump. A heat pump is basically a heat engine run in the reverse direction. So in the engine, what happens? We take the high amount of QH, then it goes to the engine. This will give some work. But here what happened? We will extract from the low temperature zone, that is the sink. It will work is given to the heat pump. This work and this low temperature heat, that is QL plus W, will become the QH, and this QH, the temperature, it will increase the temperature of the system. So where we want to increase the temperature of a room or heating of the room or heating of the system, we use the heat pump. The purpose of the heat pump is to increase the temperature from the surrounding. A heat pump is basically a heat engine run in the reverse direction. In other words, a heat pump is a device that is used to transfer heat energy to a thermal reservoir. They are often used to transfer thermal energy by absorbing heat from a cold space and releasing it to the warmer space. So here in this diagram, this you can see that here is the atmospheric in winter. Outside is heat. We want to, this is our room. We want to heat our room. So what we will do? There is a heat pump. We will operate this heat pump by the help of electric or some engine, and we will extract this from here. This heat and this work, we will add it here, and the temperature of this room will be higher. This is the TL and this is the TH. TH is higher than TL. Okay, so that is the function of your heat pump. So what is the COP? So COP is a coefficient of the performance. We don't say for the refrigerator and air conditioning or for the heat engine, because they are running in the opposite to the reverse of the heat engine. We will not say it as efficiency, because efficiency is always less than 1, but COP is always more than 1. So it is a rate of desired effect with work input. So the coefficient of the performance is desired effect divided by required input. So COP is equal to QL. So we want to, for the refrigerator, we take as a QL and divided by work in. And for the heat engine, it is QH, the higher temperature than the work done. So this will be more than. So COP of heat pump is greater than COP of refrigerator. So this is also one result which we can obtain by this principle. So what is, define the Clausius statement of second law of thermodynamics. The German scientist Rudolf Clausius laid the foundation for the second law of thermodynamics in 1850 by examining the relation between heat transfer and work. His formulation of the second law, which was published in German in 1854, is known as the Clausius statement, and he has expressed that heat can never pass from a colder to a warmer body without some other change connected therewith occurring in the same time. So heat cannot be transferred from a lower temperature to the higher temperature, because it is not a natural spontaneous process. To have this thing, we need some other changes, it should take place. That time it was not known that if you put the work, you can do that. But he told that heat can never pass from a colder to a warmer body without some other changes connected therewith occurring at the same time. Heat cannot spontaneously flow from cold region to hot region without external work being performed on the system. So we need to perform some external work. This work may be the electrical work or operation of some pumps or some engine operated systems we have to use. We have to add some work. Then only from cold region to the hot region, energy can be transferred or heat can be transferred, which is evident from the ordinary experience of the refrigerator. So to make the refrigerator cool, we have to operate a compressor, and this compressor is operating by the help of the electrical current. In example, in a refrigerator, heat is transferred from cold to hot, but only when forced by an external agent, the refrigeration system. Now another statement of the second law of thermodynamics, that is called the Kelvin-Planck statement. So the previous one is Class's statement is especially useful for the refrigeration and the heat pump, but Kelvin and Planck, it is very much useful for the engine. So here the statement of the KP is like this: it is impossible to construct a device that operates in a cyclic process and produces no effect other than raising of a weight and exchange of heat with single reservoir. So if there is a only single reservoir, you cannot do the work. So it is impossible. So the statement is starting from a negative sentence, that is impossible. So we should focus on this. What is the meaning of impossible? So explanation of the impossible is negative thought. Why? We will not try to impossible thing. We will not go for a wasting of the time. We should not go. It is wasting. Okay, so wasting of time. So we should first think that if you are having only one reservoir, means high reservoir, or the source you don't have the sink, it will not work. So it is impossible if like this. Then another term is construct a device. Construct a device, which kind of device? It should be a device operating in a cyclic process. So any device which is operating in a cyclic process, that no effect other than raising of the weight. So raising of the weight, it is not lowering of the weight, it is raising of the weight. It means doing of work against to resistance. So in the thermodynamics, the work which is against the resistance, that only we have to take for our consideration. If it is not having any resistance, the work will not be done. Like expansion, free expansion. During the free expansion, we assume that work is zero because volume is expanding, but it is not against to the resistance. It is in the vacuum. There is no resistance, so work will not be done. Another term is the single reservoir. This means that there is no heat sink in a system. QL is zero. This means rejection of heat is needed. Then only work will be produced. So if QL is not there, work cannot be done. So this eta is equal to the heat engine, the efficiency is equal to 1 minus QL by QH. If this is 1 or less than 100%, if the QL is 0 here, so it will be 100%, which is not possible. It is the by Kelvin-Planck statement. The efficiency of engine will be always less than 100%. Okay, now define the perpetual motion machine of a second kind. So perpetual motion machine means it is some assumptions or dreaming something, and you are making the machine that it will work without any input. Like if you start the engine, put the 1 liter of the petrol, after 100 kilometer, 200 kilometer also it is 1 liter. Means it is just operating without any energy. Certain machines are not practicable and are hypothetical. These machines not satisfying the second law of thermodynamics or other laws. These machines are called the perpetual motion machine. It's like fiction of Tom and Jerry and others. So you read you see some movies, they are going in Mars, Saturn, they are doing so many wonderful things. Those type of activities are perpetual motion machines, and these type of things are not possible because they are not obeying the few laws which is regulating the nature. So we have the kinds of perpetual motion machine, that is perpetual motion machine of the first kind, it violates the first law of thermodynamics. PMM of the second kind, it violates the second law of thermodynamics. PMM of third kind, it violates the third law of thermodynamics. The machine that work without friction is called the perpetual motion machine of the third kind. So now define the reversible process. We will be seeing this reversible because in all of our thermodynamics, we will see that reversible adiabatic, reversible this thing, isentropic, like this processes are coming. So reversible means it is going and coming in the same way, and there is no loss, there is no change. As it is, it has gone, it has come back. There is no change in the systems and the surrounding. Means the inside of the system is also same, and the outside also it is not varied. Then we can say that it is a reversible process. A reversible process is a process which, once having taken place, can be reversed, and is doing so leave no net change in the system and the surrounding. So there is no net change in the system and the surrounding. If it is like this, we can tell that the system is reversible. Let us say a block sitting on the ground at state 1 and move to another state 2. When moving from state 1 to 2, there is a friction between block and the ground. While moving from 2 to 1 direction opposite, but friction will be there in the same direction. Block came to the same location but heated due to the friction. So the heat Q to be removed. So the state of the surrounding is not the same as, so the friction makes the process irreversible. Okay, so that is the, if you see here, there is a block A, it is moving from here to here, and here is the ground. It has reached to the new location here. From here to here, due to this friction here, the energy is taken. So here, assume that due to the friction, it was here T1. Now it has reached to T2, where T2 is greater than the T1. Now it is again come back. So now it will be T3, not the T1, because from going to here some friction and coming also the same friction. So this T3 is greater than T2 and greater than the T1. So this T3 is much greater than the T1. So what we have to do? We have to remove this heat from here. So if you remove, this will be T1, but the surrounding, this is the surrounding. Surrounding, the temperature is increased. So it is not the reversible. Define Carnot cycle. So we have to see that very ideal case, which is called the Carnot cycle. Let us say we have a piston and the cylinder arrangement as shown below. It compresses slowly with insulation. So here this we can see that reversible adiabatic. Here also the reversible word has come. Reversible adiabatic means the heat is not rejecting. Figure 1 here. Now if we remove that insulation, transfer heat from source to system and expands slowly. So the next case is reversible isothermal heat addition. So in this second case, we are adding some heat from the source. We are adding some QH. So here this TH minus delta TH heat, it is called the reversible isothermal heat. So first one is the reversible adiabatic compression. So it is moving from here to here. As it is reaching here, we are giving some heat from the source. It is also reversible isothermal heat addition. Then it will expand, and expansion will take place at reversible adiabatic expansion. This should be insulated. Like first one, the compression, this is also insulated. Heat is not rejecting, and work is done here. Now the next one is the heat rejection. It is moving downwards. This is the TL plus del TL, and it is going here. So we have the 4 processes in the Carnot cycle. In the Carnot cycle, we have the first adiabatic, reversible adiabatic compression. Second process is reversible isothermal heat addition. Third process is reversible adiabatic expansion. Fourth process is reversible isothermal heat rejection. So what is the Carnot cycle? Fluid operates with temperature limits and does net work having all the processes are reversible with 2 reversible adiabatic and 2 reversible isothermal called Carnot cycle. The above discussion is for control mass system, but we can also find the Carnot cycle for slow system or control system. So next is the absolute temperature. Define absolute temperature. Absolute temperature is the temperature measured using the Kelvin scale, where 0 is absolute 0. The 0 point is the temperature at which particles of the matter have their minimum motion and can become no colder, that is the minimum energy. Absolute temperature, also called the thermodynamic temperature, is the temperature of an object on a scale where 0 is taken as absolute 0. Absolute temperature scales are Kelvin and the Rankine. So in this absolute temperature, this will have the minimum motion. There is a 0 energy of the system. So another name of the absolute temperature is thermodynamic temperature. So define the Clausius inequality. Clausius inequality states that in a cyclic integral of the change in entropy of the reversible system is 0. So cyclic integral of the change in entropy of the reversible system is 0. For irreversible cycle, its value must be less than 0. The entropy difference between any two states of a system can be evaluated by integral of its initial state and the final state. Since entropy is a state function, the entropy change of the system for an irreversible path is the same as for the reversible path between the same two states. So this it is the reversible or the irreversible. For the two given states, the system path is same for reversible and the entropy change will be the same. That is the, so define entropy. Entropy loosely is a measure of the quality of energy, in the sense that the lower the entropy, the higher the quality. So entropy and the quality is a reversible thing. If the entropy is high, the quality of the entropy, the higher the quality. So quality will be high. Energy is stored in a careful order way. The efficient has lower entropy. Energy is stored in a chaotic way. The random has the high entropy. Entropy is defined as the measurement of the degree of the randomness, or in other words, it is the increase in the disorganization within a system. It was designed to denote the form of energy that any energy eventually and inevitably turns into a useless heat. Clausius gave this name from the Greek word entrope, a turning point. Entropy means a turning point. For the reversible process, the universe is brought back to its initial state without changing its property. So the entropy generation for the reversible process is 0. So if it is a reversible process, the entropy will be 0. However, for the irreversible process, because of the disorder of the system, some entropy is generated. The generated entropy is measure of the irreversible. So how much more you are generating the entropy, delta S, that much it is irreversible. If delta S is equal to 0, it is a reversible, very ideal process, but it cannot go minus. That is the, as a result of this, the cyclic integral of the irreversible process is always less than 0. So the generated entropy is measure of the irreversibility. As a result of this, the cyclic integral of the irreversible process is always less than 0. So it is a minus. So define the third law of thermodynamics. The third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches to absolute zero. So by the help of this, we have find out the absolute 0 degree by the third law. So as your entropy of a system approaches to zero, approaches a constant value as the temperature approaches absolute zero. So this is the statement of the third law, which defines the absolute zero also. The entropy of a system approaches a constant value as the temperature approaches to absolute zero. The entropy of a system at absolute zero is typically zero, and in all cases is determined only by the number of different ground states it has. So entropy at absolute zero will be only zero. Next is define availability and the irreversibility. Availability or exergy. Availability is also known as the exergy. So what is the exergy? When a system is subjected to a process from its original states to the dead states, the maximum amount of useful work that can be achieved under ideal conditions is known as availability, available energy, or availability or exergy. So when the system is subjected to a process from its original state to the dead state, the maximum amount of useful work that can be achieved under ideal condition is known as the availability or the energy or the availability or the exergy. So for the given state, how much maximum energy we can use it, that is called the exergy. So if you see here, we have the here T1, and we can extract the Q1, and it is the engine, and we have to reject Q2, and it will go to the T2. So if you draw the TS diagram, so here X to Y, so this is the your T2, and this is the T1, and here is the T2. So this amount from here to here, this amount is unavailable energy. This energy is rejected. This is the rejected energy, and this is required also. You can reduce only, but only this part is the available energy, and this is called exergy. So here maximum work is equal to available energy. It is a QXY minus T naught here. This is the T naught, and here is the SY minus SX. This is the your entropy change. So this is the available energy of the system. So define unavailability energy and irreversibility. So unavailable energy we have seen in the previous plot. It is a T naught SY minus SX. It is unavailable or UAE, where SX and SY are the entropy at X and Y respectively. The available energy AE is also known as exergy, and the unavailable energy UAE as energy. The energy which cannot be utilized for doing work is called the unavailable energy. Irreversibility is equivalent to the energy destroyed, hence also known as the energy destruction. Consider the example given below. Okay, so now I will define the Gibbs free energy. So what is the meaning of Gibbs free energy? That is called the G is equal to U, that is the G is the Gibbs free energy. This is the U, this is the internal energy, minus TS. The S is the final entropy, T is the absolute temperature, plus PV, it is absolute pressure, plus final volume, and this is the work done. This is the work done. This is the energy get from the system. So we can define it is like that. Internal energy U might be thought of as energy required to create a system in the absence of changes in temperature or the volume. And additional amount of work PV must be done if the system is created from a very small volume in order to create room for the system. The Helmholtz free energy and environment at constant temperature T will be contributed an amount Ts to the system. The net energy contribution for a system created in the environment temperature T from a negligible initial volume is the Gibbs free energy. So the net energy contribution, that is the internal energy minus energy get from the system plus the work done. It is called the Gibbs free energy. Okay, so next is the define Helmholtz free energy. The Helmholtz free energy F is defined as F is equal to U minus Ts. U is the internal energy and Ts is the heat extracted. So the Helmholtz free energy is then a measure of the amount of energy you have to put in to create a system once the spontaneous energy transfer to the system from environment is accounted for. So next is the defined thermodynamic potential. Four quantities are called the thermodynamic potential, are useful in the chemical thermodynamics of reactions and non-cyclic processes. They are the internal energy, the enthalpy, the Helmholtz free energy and the Gibbs energy. And this, all the four items, that is, if you plot in a PV and the TS, PV is a vertical and the TS in a horizontal. So internal energy U plus Helmholtz free energy F, it is a U minus TS. This enthalpy is equal to U plus PV and this is the Gibbs energy, that is U plus PV minus TS. So this is the thermodynamic potential, and thermodynamic potentials are useful for the description of the non-cyclic processes. They are used along with the first law of thermodynamics. Systems work and entropy plays a major role in this, where here U is the internal energy needed to create a system, H is the energy needed to create a system plus the work needed to make room for it. This F, which is the Gibbs free energy, this is the energy needed to create a system minus the energy you can get from the environment. So it is Ts is from the environment. G is a Gibbs free energy, total energy needed to create a system and make room for it minus the energy you can get from the environment. So these are the four terms which are explained in the thermodynamic potentials. These are the references which I have taken. Any questions you are welcome to ask. Thank you very much for joining this class. Please do like and subscribe my channel. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.